That sounds like better.
So we're going to have a look at this example 1.25. So this presents us with an integral. So I is the integral along C of this linear differential form. Okay. Okay, so we might draw a picture of this to indicate the position of the 2 points. So there's the point A at 1, 2, and B is at 3, 3, 4. B is up here. So we're asked to carry out this integral, and we're told C is some curve along a path. But it's well, I mean, we might think about the straight line path between the 2 points. The straight line path between the 2 points, we'd have to think about what the equation of the line was. And that would give us a certain relationship between the x and y variables. We translate the integral into one of the variables and so on. But given that we're in the path independence dependence section, we should maybe inspect the linear differential form we're asked to integrate, okay? Because, so this is our function p here, multiplying dx, and this is our function q, multiplying dy, but, you know, they've got quite a nice something missing. No, there's nothing missing. We should inspect them because, well, there's certain similarities there between B and Q, but not a million miles away from each other. Okay. So we should check the relationship between P and Q. In particular, their partial derivatives. Okay. If we were to apply Green's theorem to this, this would relate it to a double integral over of the difference of the two partial derivatives. If you differentiate p with respect to y, we find we get 12xy minus 3y squared. And similarly, if we look at the x derivative of q, that's the other one appearing in the application of Green's theorem, look at the x derivative of q, we get, well, we actually get the same thing, 12xy minus 3y squared. Okay. So this is the criteria for path independence. Okay. So any integral of p dx plus q dy will be path independent. Meaning it doesn't matter what path we take from whatever starting point to whatever ending point, as long as those 2 points are the same, any path between them will do. Now the straight line is nice enough, but when we're integrating with respect to x and y, another path is maybe more convenient. That's the one that moves always parallel to the axes. Okay? So we might be better off coming along C1 and C2. Okay? So whatever of all the paths between, that we might take between A and B, I most like this one, okay? Because when you're moving along C1, y is always held constant. The differential dy is 0, so that kind of halves the integral, so to speak. And when you're moving parallel to the y-axis, x is held constant, and the differential dx is always going to be 0. So that's the best way to do an integral, if you can. Yes? So they're just illustrating many different possible paths that you might take from A to B. But in my mind, this one, or going up first and then across, they look the nicest for doing these integrals, okay?
C1 and C2.
Along C1 and then along C2. Yeah. Or going along a similar one up here, up and across, okay? So in my mind, C1 plus C2 looks the nicest. Okay, because along C1, y is held constant at 2, so the differential dy is 0, and x proceeds from 1 up to 3. It's very easy to say what x and y are doing. Okay, even easier than just on the straight diagonal line between A and B, where there'd be some non-trivial relationship between x and y. And on C2, it's just as easy, really. Well, easy. This stays on easy. X is held constant at 3, so dx is 0, and y proceeds from what? 2 to 4. Okay. So the integral from A to B, p dx plus q dy, is going to be the integral along C1, p dx plus q dy, plus the integral along C2, p dx plus q dy. Omitting the detail of p and q for the moment until I need it. Now I'll put in the detail of what p and q actually are. But along C1, it simplifies a bit because y is held, well, along C1, dy is 0, so I can forget about the q dy bit because it's not going to feature in the integral along C1. The only feature is the p dx, and within p, y is held constant at 2. So that's actually looking like 24x minus 8. So I'm just integrating 24x minus 8 with respect to x, and x is proceeding from 1 to 3. So that's the integral along C1. The integral along C2, I expect to simplify in a similar fashion, because along C2, dx is 0. So the p dx I'll just ignore, because the dx is 0. So I only have the q dy, and inside the q dy, x is going to be held at constant 3. It's going to be 6 by 9, 54y minus 9y squared. Yeah? dy, and y is proceeding from 2 up to 4. And so now our integral of our linear differential form is now reduced to just 2 regular single variable integrals, okay? Which we should do without much bother. So that's 12x squared minus 8x, evaluated at 1 and 3, plus 27y squared minus 3y cubed, evaluates with 2 and 4. Well, that is whatever it is. What is it? 12 nines, 108 minus 24. So Somebody tell me what that is. It's too late in the day, really. Is it too late in the day? 108 minus 24 minus 12 minus 8 plus 27 by 16, whatever that is. Minus 3 by 64, whatever that is. Minus 27 by 9, minus 3 by 8. It is what it is. I won't waste time. So those are multiplications, not decimals. Yeah. You got an answer? Final answer? Sorry? 3? 236. Okay. Not my responsibility. That's a bit from the audience. Okay. But it is whatever. Okay. So just this notion of path independence. So we now have a good characterization of it. When it was something we only discovered in examples before, that sometimes when we integrated certain linear differential forms along two different paths, same start point, same end point, we observed in some previous examples that they did give different values, and sometimes maybe that we saw we got the same value. But now we have a good characterization of it, and it's this criteria for path independence. So if these two partial derivatives of the p and the x with respect to those variables, if they're the same, it's going to be path independent. If they're the same, it means in the corresponding double integral that Green's theorem gives you, that integral is 0. So when you take two possible paths from A to B, if you run over one and then the other one, you've got a closed path. So Green's theorem tells you the integral over the sum of those two paths is 0. So the integral over one of them is the same as the integral over the other one. Okay. Which is the proof we did in this morning's lecture. Okay. Okay. So I've got some copies here. This is actually the 2014 exam paper, I believe. Just an extract from it. Six. Can I have a look at some of his questions?
Is that all the same too?
I don't feel like the whole thing from the
I just love the irony of the version when you didn't look at it.
I realized that very shame were like laughing at that.
Yeah, we were at home and then I was looking at the Snapchat. Shay pointed it out, you went, look at the moves, so I was not going to look at the movie and laugh. It was sat there for a while.
So what you've got here is, so remember in the maths methods exam, there's always two compulsory questions, question 1 and 2. One of them is question parts from my part of the course, the other compulsory question parts from Stephen's part. Then in part B, there's 6 optional questions, of which you have to do any 3. So what we've got here on this side, there's the question 1, which is my compulsory question from that year. And on the flip side, we can see all of question 3, which was one of the optional questions. Okay, and this was all about multivariable calculus. Okay. My other 2 questions one of them will be all about Laplace transforms, and the third one all about Fourier analysis. Okay. So in the optional question, there's one about stationary points. There's evaluating a certain double integral, and then there's a little, it's not that long, it's only 4 marks going for it, but a request for some explanation and information about Green's theorem. And if you look in the compulsory type question, well, I guess there's two things here from our multivariate calculus. Got an exercise about finding certain partial derivatives, and second one, a double integral over a non-rectangular region. Okay. So shall we look at parts A and B of question 1, I think? 2014, I believe. So this is one of the ones available on Moodle.
Which question are you on?
Well, I'm going to look at, we'll start off by looking at parts A and B of question 1. So part A, I mean, this is, maybe the first thing you do on the exam paper at the beginning of the 3 hours. It's, I think, if you look at the past exam papers, it's always quite doable, quite nice. But something that's very fundamental, like to the whole course, just being able to carry out partial differentiation. Okay. So we're given a function here, f of xy. It's moderately complex. It's e to the minus y times the cosine of x times y. And we're asked for these 4 partial derivatives. And it just says show how to obtain these using the principles of partial differentiation and standard differentiation results. So you're not being asked to do it from the original limit definition of the partial derivative that we did like at the very beginning. But we're just using the principle of partial differentiation. This key one where you're differentiating with respect to one variable, you treat the other variables as constants. Yeah. So the df dx would be equal to minus e to the minus y times the sine of x times y. Because when you differentiate, see, we're treating the exponential bit as a constant. We're differentiating the sine function, gives us minus sine. But the inner argument is a non-trivial function of x, so we need to multiply. We need to apply the chain rule and multiply by the derivative of that. So we get an extra factor of y. So here we're using chain rule and treating y as a constant. Again, if you can, just put in a little explanation just to demonstrate your understanding. Okay, so I'm using the chain rule on the cosine part and treating y as a constant. Okay? I won't necessarily keep repeating these, but so what would df dy be? Well, df dy is a little bit harder because, okay, we're treating x as a constant. But then when we look at this, we see it's a product of 2 parts, each of which depend on y. Okay? So that's going to require the product rule of differentiation. Yeah? So we need the product rule. So first of all, we're going to hold one of the factors the same and multiply by the derivative of the other one, which will give us minus x times the sine of xy. Because we've differentiated with respect to y. And then next, we're going to hold the other factor the same and multiply by the derivative of the other factor, which would be minus e to the minus y. So that's the justification for that is applying the product rule. Product rule for differentiation with respect to y. Yeah. Now that might be tidied up a bit, wouldn't it? Because you've got a factor of e to the minus y everywhere, and it's multiplying minus x times the sine of xy minus the cosine of xy. Yeah. Those are the 2 first-order partial derivatives. Then the 2 second-order partial derivatives that you're asked for here, d2f dx squared. Well, you could indicate your understanding here by telling me this, first of all, that the second order partial derivative with respect to x is the x derivative of the x derivative. Should indicate that. And that explains what you're doing. You're taking d dx of this up here. Okay, but again, this doesn't look that complicated in terms of x, because there's lots of y's, but there's only one place where the x is. Yeah, sorry.
You didn't do that in the course, or
Sorry?
I didn't do that in the course, or do we need to use one?
Do what?
You know, you said d2f dx squared showing that.
I mean,
understand
this
it,
line?
Yeah, but I just didn't put it down. Does it count?
I mean, if it's clear. No, because the coursework questions were more. The coursework questions were kind of you're using these principles of differentiation to achieve something higher, so to speak. So now you don't need to, as long as you do it correctly.
Yeah.
And operate it correctly, that's fine. But because this question is, it's not asking you to do a higher order thing. It's just asking you show me that you can calculate these derivatives. I think it is appropriate here. Again, you're trying to exhibit your understanding. I think it's good here to show the reader that you understand that this is what it means. So that's a good step here. But in the coursework questions, yeah, no, I as long as you do the differentiation correctly, that would be okay. Yeah.
So in exam, if we don't do that, we lose more.
I wouldn't say that. I wouldn't guarantee that.
Okay, just for.
But I think it's a good to include this kind of thing because you're showing your understanding of it. Yeah.
Right.
And remember, in an exam situation for these questions, you've got half an hour. You have to do 5 of these questions, so half an hour for each of your 5 questions, and then you've still got an extra half an hour left over for running over time and for double checking. So half an hour for each thing. I think it's time enough that you can think about demonstrating your understanding as appropriate. So that's what it is. And so, okay, there's lots of y's everywhere, but they won't trouble us when we're differentiating with respect to x. So we really just got to differentiate sine. It's going to be cosine, and we're going to get an extra factor of y from performing the chain rule. There's going to be minus y squared, e to the minus y, cosine of x times y. Yeah. The other one, on the other hand, d2f dy squared, which again is d dy, df dy. That maybe does, see, that requires the product rule again. But you see here the benefit of factorizing the thing, first of all. Because now you just have to apply the product rule on this thing multiplied by the bracket. So just one application of the product rule, so to speak. Whereas if you left it like this, you'd have to do 2, you'd have to apply the product rule to this product and then to this product. So factorizing it is a very useful step there. It shortens the amount of work you have to do. So again, product rule, keep the first factor the same, multiply by the derivative of the inner factor. Sine will differentiate a cosine, you'll get an extra x this time, so differentiating with respect to y. The derivative of the inner argument is x with respect to y. So it's going to be minus x squared cosine of xy. And differentiating this fellow gives us, well, we're differentiating minus cosine, so it's going to give us plus sine. Yeah. And we get an extra factor of x, because we're still differentiating with respect to y. So this is plus x sine of x times y. Plus what we get when we keep the bracket the same and differentiate the first factor. But when we differentiate the first factor, we get minus e to the minus y, and then the bracket is the same. Yeah. And then Yeah, there is some simplification to do there, isn't there? Yes, we might tidy this up as e to the minus y. You've got a cosine thing there. So it's cosine of xy. And we've got minus x squared minus 1. You got 1 minus x squared there, I think. And on the sines, we've got x sine xy minus, so plus another x sine xy, sine xy. So you got 2 of those. They're not cancelling, they're doubling. Plus 2x sine xy. That's just nice to tidy it up. Okay. So, that's a nice 5-mark question there. Just demonstrating your ability to apply the principles of partial differentiation and to work those out. Part B. Part B is a little bit more involved. So we're faced with a double integral in terms of the limits. So the instruction is to evaluate it by first reversing the order of integration. Yeah, because if we try to just push forward with the integration, our first step would be to perform the x integral, the inner x integral. But there we see a product of 2 functions of x, which would require integration by parts, I guess, to get the integral out. And that generates, integration by parts, you get a sum of 2 things, so it generates it longer. So it might be worth changing the order of integration, and this is what the question is asking you to do. But that is not that is non-trivial. What we'd like to do is just pick up the 2 integration processes and turn them inside out, which we would be allowed to do if these were all constants. So if those are all constants, remember, there the region of integration is a rectangle that's aligned with the coordinate axes. And the individual limits are just constants. They're unchanging. So we can just pick up the 2 integration operations and turn them inside out. But when we notice it's because one of the limits is non-constant, so it's not a rectangle. Okay? The limits for the x variable vary with the value of y. So a non-rectangular region. Yeah, so we should sketch it. Sketching would be a preliminary step to reversing the order of integration, for figuring out what the limits. So we want to turn this into a double integral, 2xy e to the xy squared, but we want to make y the inner integral and x the outer integral. So then we need to determine what these limits are. So this process will begin with a sketch. The y variable varies between 1/2 and 1. So the region of integration is to be found somewhere in this horizontal band between y equals 1/2 and y equals 1. Where exactly is it? Well, for a typical value of x, for a typical value of y somewhere, the region of the x integral we integrate along begins at the value x equals 1. So that's here. And it goes up to the value x equals 1 over y squared. So what does the value of so what does the graph of this look like? X equals 1 over y squared. So let's think about it a bit. Well, it's going to be the same for positive and negative y. You're going to get the same value of x. So it's going to be symmetric. So the curve is some symmetric curve. Under it's symmetric in reflection on the through the x-axis. Okay, because if you give this a positive or negative value of y, you get the same answer for x. And as y gets very small, this is getting extremely large. So as you get closer and closer to here, the x values are getting extremely large. And as y gets extremely large, goes up here, the x value is approaching 0. Yeah. So, and let's get a point that it goes through. It does go through the point 1, 1. And what's another point it goes to? When x is 2, y is a quarter. So quarter is down here. When x is 2, just to get some kind of, draw it reasonably correctly. When x is 2, y is a quarter. So it's just this curve which is coming down like that, right? And when x is a quarter, y is 2. So y is 2 up here, x is a quarter. That paragraph. X is a quarter, y will be 2 up here. Yeah, so, okay, that was fun, but where are we? For a typical value of y, x begins at 1. So this is the curve x equals 1. So this thing here is the curve x equals 1 over y squared. This curve here is the curve x equals 1. So x begins at x equals 1 and proceeds up to the point on this curve. So these horizontal strips begin at y equals a half, and they go up to y equals 1. So they're these horizontal strips. So the region we're talking about is this triangular looking region. It's not a triangle because this side, this hypotenuse type side is curved, so it's not a triangle. It's going to look like this. Does my graph look good? Does it look completely wrong? Oh, no, I thought you had a graphing thing. Have I messed up?
Thinking, if y is a quarter, would x not be 16?
1 over 1 over 6.
Yeah.
Oh, yeah. So, whoa.
So would it not always? Because when y
Sorry.
is a half, would it equal 4?
No, I was thinking when x is 2. Yeah, that does make, so when x is,
Am I wrong?
when x is 4, y is a half, isn't that right?
Yeah.
When x is 4, y is a half.
That's what I got.
So, flipping out. So this is x equals 4 down here. Is that right? No?
Yeah, if
Yeah.
y equals a half, x equals 4.
Yeah. So when y equals a half,
Squared, but it's fine.
when y equals a half, you get a quarter here, y squared. So 1 over a quarter is 4. So this point has got coordinate 4.
Yeah, but for it to be a quarter on the bottom, y needs to be a half.
Yeah, oh yeah, this is probably wrong. So when x is a quarter, y is a half.
I got it before now.
I just used the lower limit for y and then I think it did.
No, when x is a quarter, y is 2. If you imagine a quarter on the left-hand side,
Yeah.
you must have y equals 2. 2 squared to give you a quarter here. So that's correct.
Okay.
So the point a quarter 2 is correct. So it's just my picture should be stretched out a lot more in the horizontal direction. Because this is the point 1, x equals 1, and this is x equals 4 over here. So it's the scale is incorrect. But I think the point information is now cleared up. Does that make sense? So we've got this corner point is x coordinate 4, y coordinate 1/2. And this is still the point 1, 1. That's okay. Yeah? So we've still got this region of integration. So let's reverse the order now. So between which x values is the region contained? It's contained between x equals 1 and x equals 4. Okay? Oops, sorry. Wrong place. Ah. I can rescue that.
I'm so tired.
Okay, so the region of integration, remember we fill in the limits of integration working from the outside in. So we look at our region of integration, we ask ourselves, between what limits of the x variable does it lie? So there's parts of the region between x equals 1 and x equals 4. Then we think of a typical x value. And we'll need to integrate, well, there's this horizontal boundary is located at y equal 1/2. So our vertical strips across the region, which are located at a particular x value, they begin at y equal 1/2 and they go up to the point on this curve. So what is the point on this curve? Well, we need to turn this relation around. It's y is 1 over the square root of x. Yeah? So 1 over the reciprocal of the square root of x. Isn't that right? Yeah. Now, in terms of the limits of integration, this integral looks just as complicated as the first one. We've replaced the 1 over y squared with the 1 over square root, which is equally awkward, maybe. Expressions, maybe not. But what we have changed, what is significant, is the order of integration has now changed. So we can actually forge ahead and carry out this first integral, I think. Because this function does have a nice integral with respect to y. Now, you look at it first and it's a product of two functions of y, so we might expect to use integration by parts again. But it's got the exponential here. We know the derivative of the exponential function is itself. You operate the chain rule, then you've got to differentiate the argument of the exponential. But you notice that the derivative of this with respect to y now is equal to this factor in the front. So it is just the exponential of x times y squared. Okay? The derivative of this with respect to y is what we're integrating. Okay? So this is nice. This doing the integral with respect to y first is a lot nicer than doing the integral with respect to x first. And these limits of integration, well, one of them is the one that looked awkward, the one involving 1 over the square root of x, but you see that's going to produce something nice here. So it's going to have 1 over x here. It's going to cancel with the x. So when you do the evaluation here, what do we get? We get e, we just get e to the 1. You put in y equals 1 over the square root of x, you get 1 over x. When you put it in for y squared, that cancels with the x, we just get e, and then we get minus e to the x over 4. Okay, because to square a half, we get a quarter. And this we're integrating with respect to x. So that's going to integrate to e to the x, sorry, e times x. Minus 4 times e to the x over 4. And that's evaluated at x equals 1 and x equals 4. Yes, we can do that. This is going to give us 4e minus 4e minus e minus 4e to the quarter. So we get cancellation here. And remaining is just 4e to the quarter minus e. I believe. So that answers part B. So that was, okay, that's maybe a trickier question there. You're working harder for your 5 marks there.
Oh. The sketching that's horrible.
The sketching, yeah, you gotta.
It's just so hard. I don't like it. It's a horrible thing.
Okay, I guess we'll leave it there for this evening. We'll do a bit more. I won't forge ahead to the chapter 2. I'll leave chapters 2 and 3 to term 2. And so we'll do some more problem work and example work when I see you next week, next Monday.
Yeah.